NASA is currently undertaking one of the most ambitious and wide-reaching observation campaigns in its history, aiming its diverse fleet of spacecraft and space telescopes toward a rare traveler passing through our cosmic neighborhood. Comet 3 I/Atlas, only the third known interstellar object ever detected in our solar system. The discovery of such a body is extraordinary on its own, but what makes this event even more remarkable is the coordinated effort by NASA to gather as much information as possible from numerous vantage points spread across the solar system. Since the comet was first identified on July 1st, 12 NASA missions have already captured and processed images of the visitor, while several others are preparing for upcoming observation windows as the comet continues its journey. This massive, multi-instrument, multi-location approach gives scientists an unprecedented opportunity to compare an interstellar comet with the familiar comets originating within our own solar system, allowing researchers to study how it behaves, what it is made of, and how its interactions with sunlight, solar wind, and gravity differ from the comets that formed alongside Earth, Jupiter, and the rest of our planetary family. Every bit of data contributes to building a clearer picture of what other planetary systems may look like, and how material in distant, unknown regions of the galaxy compares to the ingredients that shaped our own worlds. One of the most valuable sets of observations came from NASA's assets stationed around Mars. Earlier in the season, Comet 3 I/Atlas made a relatively close pass by the red planet, flying at a distance of about 19 million miles. Close in astronomical terms, especially for an object visiting from beyond our solar system. This encounter provided a rare chance for several Mars-based missions to turn their attention skyward. NASA's Mars Reconnaissance Orbiter, equipped with its powerful instruments designed primarily for studying the Martian surface and atmosphere, captured one of the closest and clearest images of the interstellar comet yet obtained. Its high-resolution cameras, intended for mapping Mars in exceptional detail, offered a unique and unexpectedly useful perspective on the comet's structure and brightness. Meanwhile, further scientific value came from NASA's MAVEN spacecraft. MAVEN's mission revolves around studying the Martian atmosphere, particularly how solar wind and radiation strip particles away into space. However, MAVEN's ultraviolet imaging capabilities also make it an excellent tool for studying comets. As 3 I/Atlas passed near Mars, MAVEN recorded ultraviolet signatures that scientists can analyze to determine the composition of the comet's coma, the cloud of gas and dust surrounding its nucleus. These observations help researchers identify molecules such as water vapor, carbon compounds, and other chemicals that may behave differently in interstellar comets compared with solar system ones. Even NASA's Perseverance rover, stationed on the surface of Mars inside Jezero crater, participated in the campaign by capturing faint but valuable images of the comet. From its fixed position on the Martian surface, Perseverance offered yet another perspective, contributing to the growing mosaic of data collected from around the solar system. Beyond Mars, NASA's heliophysics missions have played another crucial role in the study of 3 I/Atlas. These missions specialize in observing the sun, solar wind, and the space environment surrounding our star. Because they can look into regions of the sky that Earth-based telescopes cannot, especially areas very close to the sun, they are uniquely suited to tracking objects that move behind or near the sun from Earth's point of view. While Comet 3 I/Atlas was hidden from terrestrial observatories as it passed behind the sun, NASA's Stereo mission captured detailed images from September 11th to October 2nd. Stereo's vantage point, located away from Earth's orbit, allowed the spacecraft to maintain visual contact even when the comet was otherwise invisible, guaranteeing a continuous record of its brightness, structure, and trajectory. In addition to Stereo, the joint ESA-NASA SOHO mission observed the comet from October 15th to 26th. SOHO, one of the longest operating solar observatories in space, is equipped to detect even faint objects near the sun and has historically discovered thousands of comets, mostly small sun grazers, that pass extremely close to the solar surface. Observing an interstellar comet like 3 I/Atlas is a novel opportunity for SOHO's instruments, allowing scientists to compare its behavior with the countless comets previously recorded in the mission's extensive archives. Another valuable contributor to the observation campaign is NASA's PUNCH mission, polarimeter to unify the corona and heliosphere, which launched earlier in the year. PUNCH is designed to study the outer atmosphere of the Sun and the solar wind using wide-field imaging techniques. Between September 20th and October 3rd, PUNCH captured images that revealed the structure of the comet's tail, providing data about how dust and gas are being pushed away from the comet's nucleus by sunlight and solar wind. Interstellar comets may have very different material properties than comets that were formed in the early solar system. By examining the tail's shape, density, and response to solar radiation, scientists can infer differences in particle size, chemical composition, and how tightly materials are bound within the comet's nucleus. Such information is crucial for understanding not only this particular comet, but also the processes that occur in star systems across the galaxy. Despite the fact that NASA and other observatories have documented thousands of comets over decades of research, the strategic, purposeful observation of an object originating from another solar system marks a scientific milestone. Prior to the discovery of the first interstellar object, 1I/Oumuamua, in 2017, and the second, 2I/Borisov, in 2019, astronomers had no direct way to study material from beyond our solar system. These rare visitors are like natural probes, carrying chemical signatures and structural features formed around distant stars. Unlike spacecraft that humans build and send outward, interstellar comets arrive unexpectedly, giving us only a limited window to study them before they accelerate out of the solar system and vanish back into interstellar space. This makes rapid coordination among space agencies extremely important. With 3I/Atlas, NASA has taken the most comprehensive and coordinated approach yet, using assets near Earth, at Mars, and across the inner solar system to track every phase of its journey. Studying an interstellar comet offers more than just curiosity or a chance to observe a rare cosmic occurrence. It helps scientists refine models of how solar systems form, how planetary bodies accumulate mass, and how materials migrate through space over millions or billions of years. Since our solar system was once a swirling disk of gas and dust like many others in the galaxy, comparing its native comets with one arriving from another star system allows researchers to understand similarities and differences in chemical makeup. These comparisons may reveal whether certain molecules are universal building blocks distributed throughout the galaxy or whether our solar system contains unique characteristics. Additionally, observing how 3I/Atlas responds to solar heat and radiation helps scientists understand the durability of materials that formed in different cosmic environments. Differences in fragmentation, outgassing rates, or tail formation could indicate that the comet experienced different temperatures, radiation levels, or collisions during its formation. Interstellar comets also contribute to the bigger question of how star systems interact. Over billions of years, gravitational forces can eject objects like comets from their home systems, sending them drifting through interstellar space until they eventually pass through another system by chance. By studying such objects, scientists can deduce information about the environments from which they originated. For instance, a comet rich in certain compounds may have formed farther from its original star, while one lacking certain materials may have formed closer to it. These clues help astronomers build a deeper understanding of planetary formation across the galaxy. NASA's global and interplanetary coordination for observing 3I/Atlas demonstrates how far space exploration has advanced. With assets stationed on multiple planets, orbiting spacecraft, solar observatories, and rover-mounted cameras, humanity now has the ability to study a single object simultaneously from widely separated viewpoints. This capability not only enhances scientific accuracy, but also ensures that no crucial period of observation is lost. Even when Earth-based telescopes are rendered useless because of the sun's glare, other spacecraft can continue monitoring the target. The result is a nearly continuous stream of data, offering a complete narrative of the comet's appearance, composition, movement, and evolution over time. The arrival of Comet 3I/Atlas is a reminder of how dynamic and interconnected the universe is, and how objects formed light years away can travel across unimaginable distances to briefly pass through our solar system. It also highlights the importance of maintaining a diverse fleet of spacecraft, each with its own specialization, because any of them might one day be perfectly positioned to observe something extraordinary. As NASA continues analyzing the images and data collected from its many missions, scientists hope to gain insights not only into the origins of this particular comet, but also into the broader processes shaping planetary systems across the galaxy. For now, 3i/Atlas serves as a cosmic messenger, offering humanity a fleeting glimpse into the countless other worlds that exist far beyond the reach of our current spacecraft, yet close enough, for a moment, to be studied, recorded, and understood.